So, an earthquake is any vibration of rocks under the ground, but an earthquake can last a long time. It can store up different amounts of energy, it can do different amounts of damage. So, just because you have an earthquake doesn't mean really anything. But a severe earthquake, of course, can cause damage to property and loss of life, and it's serious and worth understanding and investing in. So this section is looking at basically how do you measure them and how do you find out where they are. So there are a lot of parts to this. So the first is the Richter scale, and a lot of people know this, that the Richter scale is how you would measure earthquakes. An earthquake is, the scale is not linear, meaning that a 2 is not twice as much as a 1, and it is actually exponential. We're going to see that it's numerical, so you have a 1 and a 2 and a 3. You can have earthquakes of 8, you can have earthquakes of 9. A 10 would be like complete total devastation. But you can have major earthquakes in the 8s. And so what you're going to see is that every time you go from one number to another, it's actually exponentially higher in energy release. So it's like 32, I think, times more destructive, more power. So it's hard to go from a 6 to a 7 because it's not just a little bit more, it's a tremendous amount more. And a 7 to an 8 is way more than a 5 to a 6. So the longer you go, the harder it is to get that big. And so you do not have lots and lots of major earthquakes. You've got lots of little tiny ones. In fact, it's really good to have lots of little tiny earthquakes. In countries that there's numerous earthquakes every single day, they don't normally have huge earthquakes because they're releasing all the energy. There's very little energy that's storing up and up for a big event. You have little releases of energy all the time, and so you're really not piling it up. Imagine instead of pulling back a rubber band all the way and letting it go, you're just pulling it a tiny bit, let it go, tiny bit, let it go. And so you've got lots of teeny little ones rather than a big earthquake to deal with. So the magnitude is the energy released, okay? And it has to do with magnitude and amplitude. So the biggest wave, the biggest seismic wave, the amplitude of the biggest seismic wave in an earthquake, okay, and how much energy is released. So if you remember the seismogram, the amplitude is how high away from the base level it is. And so when you are looking at the S waves are the ones that are shaking sideways and up and down, and so they're the ones causing the most damage. So the amplitude of that largest one is taken into consideration. And then each number, okay, represents an amplitude of a factor of 10, and that amount of energy is actually 32 times increase in energy for each number. So from going from a 2 to a 3, from a 3 to a 4, it's 32 times more, okay, of energy. A different way of looking at it is called the moment scale. And the moment scale is how much land, the area of the plates that are touching, how much land is touching compared to how much slipped. So when you measure where a fault line is, and then after an earthquake where it is now, how much land actually slid for how much? That is an indicator of, if that can be measured. If it's high enough to where you can actually look at how much land actually moved, and how much of those rocks were touching together under the ground, if you could make guesses, then that would give you some idea of the energy that was released. Because how much energy does it take to scrape two huge plates of rock across each other, vibrating all the rocks inside the earth at the same time? The modified Mercalli scale is more of the idea of damage. So it goes up to I think it goes up to a 12, and each one is more severe than before. So you have moderate, strong, moderate, then severe earthquakes, depending upon whether or not there's damage done. So it's possible that you could have a Mercalli of 1 and not even know that you had an earthquake. Nobody in town, maybe a few people up in a tall building might know, and nobody else would know. But then you get to something more than a 10, and you've got major, major destruction. So the intensity is closer to the epicenter. You're going to have more intensity because that's where more of it's violently shaking. The farther away you get from the epicenter, the less shaking you're going to have. Also, it has to do with where the depth was. So is the earthquake directly under the ground, or is it deep, deep under the ground? So if you have very, very deep earthquakes, it is possible that you could have a violent earthquake and not have a tremendous amount of damage done on the surface because that entire continent is absorbing that energy. But if you have a shallow focus, something close to the Earth's surface, then yes, you will feel it more dramatically. And I alluded to this in the last lesson of locating an earthquake. Triangulating, as called it. So there are numerous seismic stations all over the world that are continuously monitoring earthquakes and in real time. And as you do simple, basic arithmetic with the time that the P waves come to that seismic station, and then the amount of elapsed time before the S waves come, you can determine the speed of that wave, or if you know the speed of the wave, you determine how far away that epicenter is from your seismic station. So in this picture, I've got a seismic station in Salt Lake City that recognizes that it's 1,800 kilometers away, but doesn't know where. It could be under the Pacific Ocean, it could be in Canada, it could be in Mexico, who knows? The only thing that they know is that at the speed of a P wave, at the speed of an S wave, it took so much time for that to happen, then it must be 1,800 kilometers away. So there's simply a circle drawn around Salt Lake City at that distance, and then other stations are also making measurement, and then wherever they are, they're going to draw a circle. And if you have 3 circles, that's called triangulation. If you have 3 circles, you can determine exactly where that the shaking was, because that shaking had to go to those 3 different locations, which were 3 different distances from that epicenter. And so you can triangulate and know what that is. And then the time of the earthquake is very easy because you simply take the time of the shaking. You have a seismogram at these various stations that started shaking at a certain time and ended shaking at a certain time, and that's how long that the shaking actually lasted. Now, we've looked at the belts of volcanoes and saw that that there was a circle of fire or a circumpacific belt. This same circumpacific belt is also a place where you're likely to have earthquakes, because what's happening is that you've got a plate there. The Pacific Ocean has a plate that it's sitting on, and it is being subducted underneath the continents around it. And so as it's going down under it, it is rubbing against these other plates and either being sunk down under, and then they get caught, the rocks get caught, and then it keeps shoving, and eventually it breaks that whatever that's breaking, whatever it's impeding it, and lots of energy is released, and that's an earthquake. Or you have, in the case of, say, California, North America is heading maybe south, and the Pacific Ocean, along with a little bit of the land in North America, is heading north, and that doesn't do well when you have 2 things grinding at a fault slip. And so you have lots and lots of earthquakes at this region called the Circumpacific Belt.